All right, today I would like to review midterm 2 and specifically a problem that we had in midterm 2, just to demonstrate that there are some subtleties and some of you got stuck with this problem or didn't do it completely correct. So if you consider, so what was the problem? There was an electron which was deaccelerated with a certain deceleration, with a certain acceleration, and we were asked to find the energy loss because of the radiation of electromagnetic wave from this electron. Okay, so the way I thought you would approach this problem, and this is how we solved in the problem number 5, in the homework number 5, is that we have this Larmor equation, right, in non-relativistic version of it, which included here the electric dipole moment and its second derivative of electric dipole moment with respect to time, and then electric dipole moment for a point like for the single charge can be just written in a very simple way. Okay, so the density of charge is proportional to the charge times the delta function, which just describes the trajectory of the single electron. And therefore, this electron dipole moment is given by this equation. Since we have uniform deceleration, by taking two derivative of this equation, right, we'll just get a constant, right? It will be just proportional to the vector of the acceleration. Proportionality constant is the charge. So far, so good, right? So far, everything should be everything should be clear. So what we do next, we take this equation, we substitute it into the power, we get that the power is a constant, right? So because this quantity is a constant, acceleration is time dependent, it's uniform acceleration in this case, and there are no other time dependent coefficients in this equation. So the power is a constant, is time independent, and we got the following expression for it over here. Okay. Now this white is pretty easy to solve it for the radiated pressure or the radiated energy. The change of the energy equals to the power, right? We can now solve it for the energy, right? We will get integral from t initial to t final, dt and power. Well, p power, radiated power in this case is just a constant. It's independent of time, and therefore we can just keep it in front. So now it is multiplies some Tf minus Ti, so that is the time which takes the electron to deaccelerate from the initial speed v0 and stop completely. And since it's a uniform, so the rate will be given by A, so we'll substitute it back into this equation, substitute the power, we get the final result. Now, some of you consider it a relativistic form of this equation, which we also derived when we consider a single charge moving, right? And we discussed Bremsstrahlung of the single charge. Yeah, so in principle, that one can also do. In principle, in practice, there will be some subtleties. You will see what I will talk about. So first of all, in this case, power will be time dependent only because this gamma factor, which appears on the right-hand side, is a function of velocity, and velocity changes as a function of time, right? We deaccelerate, so the velocity was v0 in the very beginning, and the particle stops at the very end, so v is equals to 0 at the end. So gamma depends on v, and v depends on t, and therefore now solving this equation over here would require some work, right? So again, so this is a little bit approaching this naively, but yes. So solving this equation will require some work. We have again integral with respect to dt of the power, but now this power is time dependent due to this factor gamma over here. So we have to find this integral, okay? Unless we do some non-relativistic approximation, right? And we approximate gamma. So we look at the non-relativistic limit, and the expansion of gamma in non-relativistic limit starts from 1, and the rest we ignore, right? but in this case, we just return to the answer that we got. Okay, so but in principle, if you really insist on continuing over here, you have to find this integral. Well, this integral is easier to find if we consider the definition of the acceleration. So note, I will come back into to here. Okay, I'll come back to here. Okay, so if you look at the definition of the acceleration, dv dt equals to negative a. So now that means that dt is proportional to dv, right, with proportionality factor is a. So I will just change the variables over here to simplify my problem, right? So I will have integral with respect to dv, which changes now, and the coefficient which came from this factor. And v changes now from v0, the initial velocity, to 0, right? And the integral is of this factor. This is this gamma to the power 6. I remind you that the gamma square equals to 1 minus v divided by c square. So now it's gamma to the power 6. So therefore we have here the cubic power. Okay. So now, well, one can find this integral, of course. So here I found it for you. It includes a bunch of factors over here. Okay, so it starts from v0 and then we continue on here. So the only thing which I would like to notice here is that, well, all of these corrections are highly suppressed, right? They're suppressed by c square compared to the first term by c to the 4th, c to the 6th. So a non-relativistic limit will go away, and actually at the end of the day, you will reproduce the factor that we wanted in the very beginning. But in reality, of course, if you want to do a relativistic form of this equation, one has to account for all of these corrections. Note, however, that this equation that we started with actually is incorrect either as well, right? So here one has to also actually correct this and consider non-relativistic version of our equations of motions. Okay, so this one has to be also revised, and then this final result will change. But anyway, so what I wanted you to do is just essentially to repeat the problem number 5, okay, with the version of it and Larmor equation version of it, which is non-relativistic. Okay, but in reality, one can do relativistic. One has to be careful here. One has to be careful with finding this integral. But I don't need you to do that. As I said, so all our exams are based on the homework, and that was the homework number 5, where we had an electron falling in the gravitational field. You can take a look at this again. All right, so now let me talk about the exam a little bit more. So for exam, all you need to do is to do 2 things, okay? First of all, go over your homework, excluding homework number 6, it was too complex, excluding homework number 6, and excluding homework number 7, the part about the topological insulators. That was problem number 2 in the homework number 7. Okay, so go over all your homework. There were not many of the homeworks that we had, right? So excluding number 6, excluding the second part of number 7, that really is quite limited amount. Okay, but do go specifically in details over your homework number 8. All right, this homework is essentially just a chapter or a section in the Griffiths. This section is quoted right in the homework formulation, so you can just go through this section in Griffiths. Well, you will have to still derive things in between, right, compared to what written in the Griffiths. In Griffiths, it's just really it's just kind of a summary one. One has to do a greater job to actually solve this homework number 8. So one has to do some in-between calculations, but nonetheless, so the Griffiths provides, a straightforward outline of how to succeed there. So do that. I didn't post the solution because the homework is due on April 23rd, and I'm afraid that there will be not much time left. But again, so it is in Griffiths, so you don't need to have any input from me here. So the second thing that you want to do to get successful on the exam is to go through the theory questions. There are 16 of them. there are 16 of them. Only 2 of them will appear on the final. Okay, so from 16, only 2 will appear on the final. So there will be 2 questions. Again, 2 questions, 2 theory questions. 1 question will be from the last topic. Okay, explicitly telling you that 1 question will be from the last topic. So go through the questions on the last topic. There are 6 of them in great detail. There will be for sure 1 question from the last topic, but you should know all 16 of them very well and be able to to go through them, or to write the answers on them without hesitation and without wasting lots of time, and dedicate most of your time to the homework. But again, so the homework is based, or just verbatim is your homework, and therefore I do expect you to be quite successful. All right, so now if you have any questions, or if you want to meet on Zoom, we can try and organize this. So first of all, if you have any questions, please email me. If you want to meet on Zoom with me, please email me as well. Your TA is also available. You can meet with Tiasha, your TA, too. If you want me to coordinate your meeting time, I can gladly do it. Or you just can email her. She's always on campus, and her room is indicated on Moodle. All right. Please, again, don't hesitate to email me if you have any questions.